Hi, and welcome back to our Chemistry Flipped classroom. Today, we continue our conversation about solids, liquids, gases, and solutions by jumping into solutions. So today, we're going to talk about what a solution is, as well as the components of a solution, so solute and solvents. And we're going to talk about different types of mixtures. So just a quick reminder of our classification of matter. We started on this all the way back in Unit 1, and we remember that matter can be divided into things that can be separated physically versus things that can't be separated physically. If it can be separated physically, we call it a mixture. If it can't, we call it a pure substance. So continuing down under mixtures, if we have a uniform composition, meaning it is evenly distributed throughout, we call that a homogeneous mixture. If it's not, then we call that a heterogeneous mixture. So solutions are a particular type of a homogeneous mixture. So this is where our solutions belong in our classification of matter. They are a homogeneous mixture. So solutions are made of two parts, a solute and a solvent. So the solute is the thing that is dissolved into a solution. It is usually the thing that there is less of. It is not necessarily a solid, though it very often is. The solvent is the thing that is doing the dissolving. It is the dissolving medium of the solution. So when we talk about the solute, this would be something like salt in a solution of salt water, of sugar in a drink, carbon dioxide in a soda. Okay, so these are things that there are less of. There's less salt than there is water in the salt water. There's less sugar than there is water in the soda. Our solvent is the thing we have more of. So again, water in the salt water, water in the soda. If we look at a tincture of iodine, which you may have occasionally encountered, sometimes parents will put them on injuries. More often, if you have stitches or some sort of a surgery, then your skin will be cleaned with a tincture of iodine. And so in that case, our solvent is actually ethanol. Okay, so solute and solvent, the two components of the solution. Not everything when mixed together will make a solution. And so we're going to talk about what makes things dissolve other things. And so the aphorism that we use is like dissolves like. And what do we mean by that? We mean that nonpolar solutes are going to dissolve best in nonpolar solvents. So again, it's important that we are able to decide whether a compound is polar or nonpolar, and that's going to come back to Vesper structures, to differences in electronegativity, to understanding all of that we learned about in molecular geometry. So things like fats, steroids, and waxes, those are nonpolar solutes. Most of our long carbon chains are going to be nonpolar solutes. And so some of our nonpolar solvents would be things like benzene, hexane, or toluene. Okay, and this becomes important in our everyday lives when we think about things like if you've ever tried to get the little bit of sticky residue off after pulling a sticker off of something that you've recently purchased. You might have tried using acetone to get it off. And that's because the glue is a nonpolar solute and we want to dissolve it in a nonpolar solvent. On the other hand, polar and ionic solutes are going to dissolve best in polar solvents. So these are things like inorganic salts and sugars. Those are our polar and our ionic solutes, and they're going to dissolve best in polar solvents like water, short chain alcohols, things like acetic acid. Okay, so why is this the case? Why does like dissolve like? Well, we've got to talk then about the process of solution or solvation. So what does it mean when we say that a substance dissolves? Is it different if it's ionic versus if it's molecular? Yes. Okay, so why does like dissolve like? Well, when we talk about the interactions of the solute with the solvent, if the interactions between this, so when we dissolve something, we have a couple of factors working towards dissolving and a couple of factors working against dissolving. So we need to understand the strength of each of those factors so that we can decide whether or not something will dissolve. So let's take a look at some polar solute and solvent interactions. And we're going to start with water. So in this little image, we have water molecules. Those are the red and white molecules. And we have a sodium chloride crystal. So we can see the sodium chloride crystal there, the green and gray. So in order for water to dissolve this sodium chloride, this table salt, it has to pull the table salt apart and solvate it. So our oxygen end of our water molecule is going to be attracted to the positive ion of the salt. And conversely, the hydrogen end of the water molecule is going to be attracted to the negative ion in that salt. So it's this attraction that allows water to dissolve sodium chloride. And these are really strong attractions, although hydrogen bonding is weaker, and in this case, ion dipole bonding is weaker than ionic bonds, the number of them allows them to be strong enough. So when we talk about solvation of ions, or the dissolving of ionic compounds, we really have a competition between three kinds of attractions. So we have this attraction that I just talked about between the solvent and the solute. So this is that attraction between the chloride ion and the water molecules, between the sodium ion and the water molecules. So we have those attractions, but at the same time, they're fighting the attraction of the solute for itself, the attraction of the chloride ion for the sodium ion. We're also fighting the attraction of the solvent for itself, of the water molecules for the other water molecules. So we have a competition. We have the attraction between the solvent and the solute working towards dissolving, but on the other side, we have the attraction between the solute particles and the attractions between the solvent particles. So those are working against each other. So several factors affect these attractions. So if we have smaller ions, we're going to have greater attractions. That comes back to that Coulomb's law that we learned about. And we have the charge on the ions. Higher charge is going to create greater attractions. So whether or not an ionic compound or a polar compound will dissolve really comes down to what's stronger, the attractions between the solvent and the solute, or the attractions between the solute and solvent and solvent. And so if this first factor, solvent-solute attraction, is bigger, then that compound will dissolve. If the solute and solvent attractions are bigger, then it won't dissolve. When we talk about solvation or dissolution of molecular compounds, we have the same competition between three types of attractions. It's that solvent-solute attraction and solute-solute, solvent-solvent attractions. But for molecular compounds, our biggest impact is going to come from the polarity of the solute. Polar molecules are going to dissolve in water. Non-polar molecules are going to dissolve in non-polar solvents. When we look at the solvent-solute attraction, non-polar and polar, so if you have a non-polar solute, it's not going to have strong attractions to a polar solvent. So when these attractions are similar, so non-polar and non-polar, or polar and polar, then it's going to be more soluble. So that's why like dissolves like. So when we say something is soluble, remember solubility rules where we talked about the fact that lead-containing salts aren't soluble. Salts that contain group 1 ions are soluble. All of those rules come back to this idea of solubility. So when we talk about solubility, we are talking about the measurement of how well one substance dissolves in another. And it's usually measured in grams of solute per 100 grams of solvent. And we say that a substance is soluble. So according to those solubility rules, is soluble if 1 gram of it will dissolve in 100 grams of solvent. So with the information that we just talked about, that solvent attraction versus solute, and solvent, what factors do we think are going to impact solubility? Well, for most solids, Solubility is going to increase with temperature. As temperature increases, there's more movement of the molecules. Kinetic energy is directly proportional to temperature. And so it's going to make it, and the particles are going to spread out. So it's going to make it easier for those solute particles to separate, solvent particles to get in and create those attractive forces. The rate at which solids dissolve increases with increasing surface area of the solid. So it's easier to dissolve a spoonful of sugar than it is to dissolve a sugar cube. The higher the surface area, the more contact between the solvent and the solute, and therefore the faster it's going to dissolve. This doesn't change solubility. It doesn't change how much will dissolve. It just changes how fast it will dissolve. By the same token, stirring is going to increase how fast something dissolves because you have more movement of the particles, but it's not going to change how much will dissolve. But solubility does generally increase with temperature. When it comes to liquids, solubility is only going to depend on polarity. So it's not dependent on temperature or stirring or surface area or any of that. If they have the same polarity, they're going to be able to mix. We call that miscible, and they're going to be soluble in one another. And then when it comes to gases, the solubility of gases decreases with an increase in temperature. So that means that the higher the temperature, the less soluble a gas is. And this is why we like to keep our 2 liters of soda in the fridge, because it keeps them from going flat as fast. And the solubility of gases increases with pressure above the solution. And this is why sodas are bottled at pressure. So when you open a can of soda, you hear that shh sound, and that's actually pressure releasing from the can. And that's because by keeping it bottled under pressure, they're keeping as much of that carbon dioxide gas in the soda as possible. So gases solubility increase with a decrease in temperature, and it increases with pressure above the solution. So solids dissolve best when heated, when stirred, and when ground into small particles. Gases are going to dissolve best when it's cold, when the pressure is high. Pressure doesn't impact the solubility of solids at all. Okay, so we're going to pause there. As always, I look forward to hearing your questions and seeing you in class.